All right, so let's look at a second example. So the drug 6-MP, which is 6-mercaptopurine, is used to treat leukemia. The remission time in weeks for a random sample of 21 patients using 6-MP was found to have a mean time of 17.1 weeks and a standard deviation of 10 weeks. So we're going to let our random variable x represent the remission time in weeks for all patients using 6-MP. Assume x is mound-shaped and symmetric. A previously used drug treatment had mean remission time mu equals 12.5 weeks. So does the data indicate that the mean remission time using the drug 6-MP is different either way from 12.5 weeks? And we're going to use alpha equaling 0.01. So same steps. We want to start out finding our null, our alternative, and our alpha value. So let's look at our claim. So does the data indicate that the mean remission time using 6-MP is different either way from 12.5 weeks? So you can kind of think of this as pointing out in either direction. So our claim is mu is not equal to 12.5. So because this does not have the equality, that has to be our alternative hypothesis. So then our null hypothesis always equals, so mu equals 12.5. And then our alpha value, in this case, I just flat out said alpha equaling 0.01, so alpha is 0.01. Remember that alpha should be very easy points. So now we want to figure out what type of test to conduct. So again, look at our alternative hypothesis. In this case, it's not equal, so you can kind of think of not equals as pointing out arrows on both sides. So it's pointing out in both directions. So think of this as a two-tailed test. The test statistic, so remember that's Z or T. So we want to look, in this case, the sample had a standard deviation of 10 weeks. So because we have our sample standard deviation, so we have S, so sigma is unknown. So that tells us we're going to use a t-test statistic. But we also need to check and make sure central limit theorem applies. So is n either greater than or equal to 30, or is the original population distribution normally distributed? So here in this case, our sample size is 21, so we're not bigger than 30. But we're told that the x is mound-shaped symmetric, which typically is just another way of saying normally distributed. So that checks our box for us. So the population is normally distributed. So then now we want to calculate our t-statistic. The nice thing is the t-statistic, the formula is really no different than calculating your z-test statistic. The only difference is which standard deviation you have. So to calculate your t-test statistic, it's the sample mean minus the population mean divided by the standard deviation we have, which is S over square root of n. So now if we think about that, so x bar, our sample mean, is 17.1 minus our population mean, which we're told mu not equal to 12.5, divided by the sample standard deviation of 10 weeks over the square root of our sample size, which is 21. So if we calculate that, we get 2.11. So now we want to find our p-interval, or our p-value. So remember, if it's a t-test, we're normally going to end up with a p-interval here. So in this case, it's usually going to be the interval containing the p-value, since we have a t-test statistic. Now remember, if you're doing a t-test statistic, you need one additional piece. We need our degree of freedom. So remember, degree of freedom is always n minus 1. So here, that's going to be 21 minus 1, which is 20. And if your degree of freedom is not on the table, remember, just go up to the next smaller degree of freedom that's on the table. So here, we're going to look for our degree of freedom 20 on our t-table. So we know we're going to be somewhere on this row. So degree of freedom is 20. And now we're looking for, ideally, our number. So our t-statistic in this case was 2.11. Now if we look on this row, we have 5 numbers. 2.11 is not there. So because 2.11 is not there, let's do kind of the same idea of what we did when we did inverse normal. We want to look for the 2 numbers that are closest to 2.11 on our row. So if we look here, 2.11, that's going to be somewhere in between 2.086 and 2.528. So then we're going to follow those 2 columns up to the top to the row for the area in however many tails that we're doing. In this case, we are doing a 2-tailed test, so we want to go to the area in 2 tails row. If we were doing either a left tail or a right tailed test, we would go to the area in 1 tail. And so we look, and the top of those 2 columns on area in 2 tails are 0.050 and 0.020. So our t-statistic has a probability somewhere between 0.02 and 0.05. So be careful. You always want to look at this in numerical order. So if we look, you've got to read these values from right to left to have it in numerical order. So our p-interval, so the interval containing our p-value in this case, is going to be 0.02 to 0.05. So 0.020 is somewhere less than our p-value, which is somewhere less than 0.050. So in other words, our p-value is somewhere in that range between 0.020 and 0.050. So now we want to conclude our test. So we're still using that same criteria. If p is greater than alpha, then we do not reject the null. But if p is less than or equal to alpha, we reject it. In the case where you have an interval, if any piece of that interval is greater than alpha, doesn't matter if it's just the tiniest piece, if any piece of that interval is greater than alpha, you have to fail to reject. So in this case, 0.020 is less than p less than 0.050. That entire region as a whole, how does it correspond with our alpha of 0.010 or 0.01? So since alpha is smaller than our smallest end of this interval, alpha is smaller than that entire interval. So that entire p interval is greater than our alpha. So because of that, we fail to reject. So since our entire p interval is bigger than alpha, we have to fail to reject. And so now we want to interpret this in context again, so putting it back into words. So if we go back to our claim was our alternative hypothesis. Now we said we fail to reject the null, so we have to stick with it, so we can't say that we support that claim, right? So there is not enough evidence. to support the claim that, in this case, again, what are we testing? The mean remission time using 6-MP is different from 12.5 weeks. And as always, include your alpha level, so at the 1% significance level. And that's all there is to putting it back in context. So the nice thing about critical regions, you're going to get a definite answer. So if we look at our critical values here, what we want to do is we want to kind of do the opposite of how we just found our p interval. So now we know we're doing a area in two tails, and we're testing this at the 1% significance level. So we're going to go up to area in two tails, find our 1% significance level, so 0.010, and we're going to follow that down to our degree of freedom row. So that number, in this case 2.845, is going to be a piece of our critical numbers. So if we want to figure out which one to take, because the t-statistic, since it's symmetric like our z is, it only shows the positive numbers. But remember, I said if it's two-tailed, you're going to end up with a positive and a negative number. So if you forget which one you need, look at these pictures on the right-hand side of your t-table. And they're going to tell you what sign to take. So in this case, we're doing a two-tailed test. So if we look down here, it tells us, okay, we need negative t and t. And it's actually sketching for your conclusion for you. So in this case, because we want negative t and positive t, then we're going to take both values of our sign here. So we're going to take tc to be both positive and negative 2.845. And so then we want to conclude our test. So we draw the sketch the exact same way that we did for our z distribution, just remembering that there's a little bit more space in the tails. So TC is 2.845 and negative 2.845. So negative 2.5 is our negative value. Positive 2.845 is our positive critical value. And we want to shade in the tails, so everything on both sides, so to the right and to the left of those two numbers. And those, our two regions, are our rejection region. And then everything in the middle is our fail to reject region. So now we put our test statistic on there. So our test statistic was t equal to 2.11. which lies in the fail to reject region. So we do not reject, or we fail to reject. So we fail to reject the null, since t equaling 2.11 lies outside the rejection region. And that's it. It's worth mentioning, you will usually get the same conclusion with both methods. The only time you may not is if you're doing a t-test by hand and your p-interval, the interval containing the p-value, is kind of borderline with your alpha. So maybe part of that interval falls in greater than alpha, so then you were forced to fail to reject. So depending on which side of the interval your actual p-value is closer to, then you could possibly get a different answer using critical regions. In this case, critical regions would give you a stronger result, so I would trust that answer better. If you're doing a z-test, it really makes no difference. You will get the same answer regardless.